So far we were talking about a predicate logic, and we were talking about how to write things in that language. But now that we master the art of saying what we want in logic, let's see what we could do with the things that we say. And one big thing that we could do in predicate logic is to prove all sorts of interesting things, all sorts of statements. So the next several lectures, we are going to talk about theorems and proofs and axioms and scary things like that. We are going to talk a lot about definitions, which is one of the very, very big things that you see in computer science all the time. And as we are talking about it, keep in mind that the goal is not to prove specific things for the sake of proving them. It's not to memorize specific definitions for the sake of knowing them. What we are trying to do here is to understand what goes into a theorem, what goes into a proof, which things need what. And with definitions, we are trying to learn a very useful skill for computer scientists, the skill of understanding when somebody is telling you, oh yeah, I need this thing that kind of looks like that and does this kind of stuff. And then you'll have to look at it and say, okay, this is how I can write it formally. Is it right? Is it not right? And this is how much time and work it would take. And this is how I can actually program it. So here we're trying to make the very, very first step towards that lofty goal in talking about the words and the concepts that we are going to be using, in particular proofs, theorems, lemmas, and axioms. So, theories and theorems. Those two sound similar, but they're somewhat different things. So when we in computer science and people in mathematics too talk about theories, they mean that they have some axioms, some properties, and then they kind of consider everything that can be derived from those properties. In mathematics, the theories that you see are things like geometry, set theory, theory of integers. In computer science, you see a lot of additional theories. For example, a theory that talks about programs and their memory accesses. Okay, now a theorem is just something in a theory that's true. And usually when we talk about theorems, it's something that we could actually show that it is true, proof from axioms. So what are axioms? That's sort of the description of a theory. Those are the rules that tell us what the theory is like. So in a theory, we'll have some objects like numbers or lines or sets or programs and arrays. And we have some rules that tell us what happens. For example, a rule can tell us that if you write something in memory and then you read from the same place right away, then you expect to see the same thing that you've written. Otherwise, programming would be really hard. So one thing about theorems and theories is something that can be true, or a theorem in one theory can be completely false in another, even if they're talking about similar things. So here is an example. Suppose I say that between any two numbers there is always another number. Is it true? Is it false? Well, if you're talking about real numbers, then it's easily true. Just sum them up and take the average. It's in between of the two. But if you're talking about integers, well, try to find me an integer between 1 and 2 doesn't work that way. So this statement, between any two numbers there is another number, is a theorem for the theory of real numbers, and is actually false in the theory of integers. So if there is one list of axioms that you might have seen, that's probably the axioms of geometry, the famous ancient Euclid's postulates. Greek liked mathematics and theory and theorems. So here are the 5 statements, and then out of those statements, pretty much all the geometry as we know it, Euclid geometry, can be derived. For a very, very long time, people were thinking that they can derive the last of those statements, the parallel postulate that says that through a point you could draw exactly one line parallel to some other line. They were trying to derive it from the rest, and they didn't succeed. And then two mathematicians came up with axioms of geometry, of different geometries, where this postulate was just not true, but everything else worked. So one example was, imagine that you're not drawing lines on a flat surface, but you're drawing them on a sphere. Look at the pole of that sphere if you look at it as Earth as a sphere. Do you see lines that were parallel and the equator all coming together? Well, if your geometry is on the surface of the sphere, you could still have a geometry, but that won't be Euclidean. So you will have different axiom, at least one of them will be different, the last one, the rest stay the same. And you will have different theorems. The things that are true for geometry on the surface on a planet are not really true when everything is flat. So let's look at something a little bit more familiar. This slide should look familiar to you from the very beginning of the course. When we were talking about propositional logic, we say that here are some rules or qualities that are true about propositional logic, and we could use them to simplify formulas and sometimes to show whether a formula is a tautology or a contradiction. Well, guess what? We could think about a theory of propositional logic where the object it deals with are logic formulas, connectives, and so on, and where rules, the axioms, are exactly those equalities that we considered. For example, that if you take a formula or its negation, then this is always true. We didn't call it a theory, but it is a theory, and we could prove all sorts of things in it. So one caveat about proofs, something that I don't know if somebody have told you before or not, but when you are reading a proof, unless you are reading some very, very, very logic set theory book, chances are not every single step and little detail will be spelled out. And one of the crucial skills that you'll want to pick up when you're trying to read and understand proofs is if you are going through a proof and some step seems to be like a long jump, you could sit down and from your knowledge, which is different from the knowledge of the person who wrote the proof, from your knowledge try to fill in that gap, try to make a little bridge to the other side of that gap so that you don't need to make the big jump. A lot of time when you see people trying to figure out what something is and how it works, you see them writing little examples, trying to say, oh yeah, this goes from this because, okay, I can think of this and this and this reason. And this is how they fill in the proof so that all details will be understandable to them. That said, when you are writing a proof, try to put enough details to make it clear. Try to make it so that if you give it to your friend will say, okay, yeah, I can see why every step works. So that said, this is proofs in real life. But here, as we are just beginning to look at the proofs and how they're structured, just beginning to get the intuition for what those things look like, we will try to spell out as much detail as we can. We try to show the logic behind the proofs and why things in the proofs look the way they are, using our knowledge of logic and how things work.